Hi Josh, can you do this problem in uh, differential calculus? Graphs of dy, dx, and second derivative of function y is f of x are shown in the diagram. The function of y is equal to fx passes through the points 1 and -2, 4 and 5, and 6 and 2 without finding the equation of the function y is equal to f of x. First, determine the coordinates of the maximum and minimum points of the graph of y. Second, sketch the graph of the function y is equal to f of x. What does this problem mean? You will solve it by
Observation.
observation, yes.
So assuming that the
It's
graph
a different
here,
color of pen.
the graphs here are accurate. dy dx is not shown here. X. dy dx is 0 when x is equal to 1, 4, 6. So this means the stationary any stationary point of any function is stationary when dy dx is equal to 0. So therefore, the x of this function f of x, the dy dx, which is its derivative, when it is 0, those are the points at which dy dx is equal to 0. Those are its stationary points. So here, dy dx is equal to 0 at x equals 1, 4, and 6. So therefore, the stationary
Slow down, not too
points,
fast.
the stationary points of f of x have x's 1, 4, and 6.
6.
Okay. Now, to find what is the minimum and maximum when put in red, when d squared y over dx squared is greater than 0, it is a minimum. It's a minimum. And when it is less than 0, it is a maximum. So here are our points that we have chosen. 1, 4, and 6. From what appears apparent in the graph.
It's a different color.
It looks like whatever one is on the second derivative is positive, and here it is negative. Yes, I will put it. And here it is again positive. So this is positive,
yes.
negative, and positive. So again, as I was saying, when it's greater than 0 or positive, then it is minimum. And when it is less than 0, it is maximum. So I can easily put this here. Luckily, the problem already states the y of the points 1, 4, and 6. Rather interesting coincidence. Anyway, so I will put it here. X at 1, which is 1, -2. This is positive, so therefore it is a minimum. 4 is negative, so 4, the second derivative is negative, so therefore it's a maximum. This is maximum. And like earlier, 6 has a positive second derivative. When x is equal to 6, the second derivative is positive. So therefore, it is a minimum.
Minimum. Can you record? Highlight this. That is for I. For
Okay.
double I.
For double I will sketch the
graph.
graph. Okay, now so I've prepared the background, and this is our. I will just copy this. Cut. I will prepare the graph. Starting from here. Oops. Even smaller. This has to fit everything but big enough. Why? Some are eyeballing in the middle. Here. this x, found that x should not be very big because it will be hard to draw the curve. We're not given information on what is before, what is what is
You can
before.
put the other graphs here on the right side if you want.
Yes. This will be used as a reference. We now set the scale. One. Where the significant points are from 0 to 6. So 1, 2, 3, 4, 5, 6. Too small. 1, 2, 3, 4, 5, 6. Perfect. Okay, good.
Yes.
1, 2, 3, 4,
What's that?
5, 6. X.
X. Yes.
And this is why the maximum, what's the maximum? 5. So we only need 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3. Smaller. 1, 2. Even smaller here. 1, 2, 3, 4, 5. Negative 1. What is the smallest? No, it's the smallest. Negative 2. So I'll just use until say negative 3.
The numbers, please.
Okay. So now I'll just plot those points. It was 1, negative 2. 1, negative 2. Huh? This one here. 4, 5. 4, 4, 2. Right, and this is the guide. Okay, good. And then what? The other one? 6, 2. 2, 7.
Points plotted.
Okay. So now this is the harder part.
Can you make them more conspicuous? The points.
What's this? There's a 3 point. Okay. So, back. Now, from the graph dy dx, this means that it was the dy dx essentially is just the slope at all of the points. So here, before 0 and 1, in between 0 and 1, it was negative, 0, positive, sort of like a table of signs. And then we note these points where it sort of changes. It's like an inflection point. So here at 0, there was sort of an inflection point. Here, there was another one. So this means the concavity of the graph changes. For example, let's say our graph looks like this. Where does the concavity change? Around here, maybe. It changes from concavity downwards to concavity upwards. So the dy dx graph would sort of look like this. It was negative, and then it became positive. And then of course it became negative again because there was another one here. So essentially here, what I mean is that it is this was a smooth section of curve going upwards. Then the concavity changed. It means now it is moving downwards. So it is sort of a peak. Okay, so here 2, at 2 it is positive. In between it is also positive.
At 3, is it positive?
Yes, it's still positive. So now this is 0, negative, 0, positive. Okay. So what I can draw from this is that it starts from 1. We don't start from 0 yet because that's harder. I will start from 1 first. Imagine this does not exist for some time. I will start from 1. It will go up until it reaches 4 because this is all positive. It will go up until it reaches 4, and then from 4 it will go down. It will become negative. It will go at 6. It will become 0, and it will start going
But
upwards.
around 2 point
Around 2.5
between 2.5 is the
is the inflection point. So okay, so I will just first point it out. What I mean is that it will look sort of like this. Now this is still this. So here the concavity is downward. So you can see. Wait. Around 2.5. At here the concavity is downward.
so at around 2.5 those
Now it's
where are
at around
the
2.5 the concavity changes to upwards. Like this.
minimum and maximum of that curve?
Yes? And I'll try to perfect it. So at around 2 between 2 and 3 with maybe around 2.5, maybe this little wrong. Should be around 2.5. The concavity changes from going like this, a downwards curve. Up, it's sort of an opening upwards. And then here it changes to an opening downwards. Because here the slope of the dy dx, that is the d squared y over dx squared. When it's moving upwards, it means it is opening upwards. When it's moving downwards, it's opening downwards. This sort of inflection point on the dy dx just means that it is switching from opening upwards to opening downwards, like in this figure. Okay. Now, I will uncover this. We have another inflection looking point at 0. I don't actually I do not know if that's an inflection point because maybe the inflection point is here and then it goes up. But yeah, so I don't really know. But assuming that that's the inflection point, will sort of look like this. Really, can be anywhere. And then it will change at 0. It will go from opening downwards to opening upwards. But since I don't actually know any of that, I will just use a dotted line because it is unknown whether that is actually the inflection point of this dy dx curve. Just a dotted line for now. So now, they're around between 4 and 6 or around 5 maybe. There's another inflection point in the dy dx curve. So around here, it will change from this one. It will change from opening upwards to opening downwards. And then since here after 6, the slope is upwards again, it will open upwards. So I don't know the why of the, well, I don't know why because it is asked in the problem without finding the equation of the function y equals f of x. So I have no clue where what y5 is in, or if that's even 5 where the inflection point occurs. But assuming it's approximately there, this is opening upwards, opening downwards, and then at around 5, it will start opening downwards until it ends at 6, because at that point the dy dx, or the slope, is already 0. So here is the slope is 0, and then it will go up again, and then it's opening upwards. I don't really know at what rate. Here it seems to, the graph doesn't continue on the d squared y over dx squared after 6, so I have no idea what this is supposed to look like. So I'll again put it with a dotted line, but approximately it should look like this. Then maybe once we use integrals, we can find out the actual equation of the function. Once we do find it, you can actually graph it. Let's see. Hopefully, it will look like this. But this is just an approximation. So you can see we don't know what is behind 1 and what is after 6. But it looks like this. So I will again put in the middle of 2 and 3 approximately. It changes concavity here. At approximately find also changes concavity. So the graph approximately looks like this. I'll just put the green mark.
Okay.
Okay. So thanks for watching.
Thanks for watching.
I hope you learned a lot. Bye.
Okay, bye.